So today we're going to have a presentation on chlorine and UV disinfection applications for small water systems. This webinar will focus on the common disinfection technologies used by smaller water systems to meet the treatment objectives outlined in the BC Drinking Water Protection Act and regulations, with an emphasis on ultraviolet disinfection and chlorination as a dual barrier. So Grant is going to talk about how these technologies work, the advantages and disadvantages of each one, typical equipment involved with each approach, operational best practices, maintenance requirements, and troubleshooting. So you may want to take notes, but actually we will be sharing his presentation afterwards. For this webinar, we're going to do our questions a little bit differently. Please feel free to post your questions as they come to you in the questions box, and we will be taking periodic breaks. Grant's going to take periodic breaks throughout the presentation to answer your questions so that they're not too far from the context that they belong to in the presentation. Just a little bit more about Grant before we start. Grant has been involved in water treatment for more than 20 years, specializing in small systems and UV disinfection. He is a co-founder and currently serves as the CEO of Home Plus Products Incorporated, a Kamloops-based wholesale distributor of water treatment products. He has a Bachelor of Business Administration from Simon Fraser University and is accredited by the Canadian Water Quality Association as a certified water technician. He's worked extensively with public health authorities and other stakeholders in Western Canada to promote best practices in the application of water treatment technology for small communities and other regulated applications. He has been a guest speaker at a variety of conferences and events for the Ontario Health Authority, Vancouver Coastal Health Authority, Island Health Authority, Alberta Health Services, and the Canadian Water Quality Association, the Small Water Users Association of BC, the BC Institute of Technology, and more. He currently serves on the Education Committee of the Canadian Water Quality Association. So this session will take approximately an hour with a half an hour afterwards for questions. And actually, sorry, as I said, we'll do the questions periodically through the session. Okay, I'm going to hand the presentation over to Grant because that's why you guys are all here. Okay.
Good morning, everyone. This is Grant here. I'm just going to get my presentation up on the screen momentarily here. Okay, so hopefully everybody can see that. Thank you for the introduction, Natasha. I will do my best to get through a lot of content here. I was saying to Natasha and Mike earlier that this presentation is normally done over a whole day, so I've tried to condense it down to something that we can cover relatively quickly in an introductory type session. If you have any additional questions afterwards, beyond what we're able to cover today, I would certainly be more than willing to speak with you to answer any individual questions that you have and so on. So if we are unable to cover a topic in depth today that is of interest to you, feel free to reach out to Natasha or Mike. They'll put you in touch with me, and we can make sure that all of your questions get answered. So Natasha has explained the agenda, I think, quite well. We're going to talk about how UV and chlorine work, and in particular how they work together to achieve our directives under the Drinking Water Protection Act and regulations. We'll talk about the advantages and disadvantages of each technology, what the actual physical equipment looks like and how the components work together. We'll certainly talk about installation, operation, and maintenance, in particular best practices in each of those areas. And then probably one of the areas that you'll be most interested in talking about is how we deal with some of the more common problems with these types of systems. And certainly I won't be able to address every type of situation, but we'll try and address some of the ones that we see most frequently and that cause the most amount of operational grief. So what is the whole point of this? Well, we have in British Columbia our 43210 drinking water objective. This is set out in the Drinking Water Protection Act and regulations as our minimum acceptable treatment standard. I'm sure many of you have heard of this standard before. Key to the standard is that we are always looking to achieve, wherever possible, 2 barriers of protection. And this is where UV and chlorination can work very, very well together to achieve the other directives in this objective. So we're looking for the 4-log inactivation of viruses, 3-log inactivation of crypto and giardia. We're aiming to have a very low level of turbidity because we know that turbidity interferes with our disinfection processes otherwise. And of course, we want to see 0 bacteriological indicators. Now, one thing that is important to note is that this objective, while seemingly relatively precise, does leave some room for interpretation. And there are some minor interpretive differences between the various health authorities in the province, particularly as it relates to the first requirement for 4-log inactivation of viruses. The definition of which virus becomes quite important, particularly when you're looking at UV disinfection, as we'll learn. And not all of the health authorities are using the same virus target for that standard. We'll talk a little bit about that. So I'm going to start off by covering UV technology first. One of the reasons for that is it typically does come before the chlorination step in our treatment process. And it also happens to be my area of particular expertise. I've been working in the area of UV for about 23 years now. That said, we're always learning new things about the technology as well, and it continues to advance. And in fact, we'll see some exciting developments on the UV front in the next few years. I'm going to use a very simple analogy when I'm talking about UV disinfection, and that is the analogy of our own personal exposure to UV light through sunshine and its ability to cause a sunburn. When we're talking about the UV spectrum of light that we're using in an ultraviolet sterilizer, though, it's a little bit different. We're focusing on the UVC spectrum as opposed to UVA and UVB, and a very, very specific wavelength, that 254 nanometers. This particular wavelength is very, very close to the optimal germicidal wavelength that causes the most damage and harm to bacteria and viruses. And essentially what that UV light is doing is it's breaking and damaging the DNA chains inside the microorganism, rendering it unable to reproduce. So we don't generally refer to this as killing bacteria or killing viruses. We typically use the word inactivation. We're sterilizing or neutering the bacteria and viruses and other microorganisms so they can't replicate, and if they can't replicate, they can't cause illness. This technology can be used across a very, very wide spectrum of different applications, from something as simple as a small UV sterilizer underneath the kitchen sink that provides water to one faucet, up to municipal water treatment and wastewater treatment systems. The largest UV sterilizer installation that I'm aware of in the world right now is in New York State, and it treats 2.2 billion gallons of water per day. And the UV reactors, or the chambers in which the UV lamps are located, are large enough to walk around inside. So the technology technology, excuse me, is very, very scalable to larger applications. Now, the effectiveness of UV disinfection is determined by what we refer to as dosage, which is a function of two key parameters, the intensity of the light and the exposure time to that light. And I'll talk a little bit more about that in a moment. So UV has a couple of really key advantages. Most notable, and this applies to achieving our 43210 objectives, the 3-log inactivation of crypto and giardia. UV is much more effective at inactivating that particular class of contaminants as compared to chlorine. And as we'll learn, chlorine is more effective at certain, or the inactivation of certain more resistant viruses. So the two technologies really work well hand in hand because they target different microorganisms to a certain degree. They're both very effective at inactivating bacteria like E. coli. One of the beneficial things of UV is that it does not alter any other physical parameters of the water other than potentially water temperature very slightly. It doesn't change any of the other attributes like taste or mineral content. It does not form disinfection byproducts. Some of you that have organic matter in your water, when you chlorinate, you may be faced with challenges of byproduct chemicals like trihalomethanes or haloacidic acids forming. We don't have to worry about that with ultraviolet light. It's fairly simple to install and operate. It's energy efficient and cost effective. It's physically quite small, and there's no chemical handling requirements. But it has its own limitations and important considerations for operations. We have to be very careful to ensure that we're meeting the pre-treatment requirements set out by the manufacturer of the equipment. We'll talk about a few of those common ones in a moment. We need to make sure that we do preventative maintenance. The frequency of that will be determined largely by the water conditions, but it's not something that we can neglect and expect to have it keep operating efficiently and effectively for us. As I mentioned, there is some resistance of UV disinfection from certain resistant viruses, so it's not that effective at inactivating certain viruses, unlike chlorination. Very, very important is UV disinfection is a point source disinfection method. It disinfects at a particular point and there is no residual downstream treatment. So if there is any failures within our distribution system or weak points, cross connections, those sorts of things within our distribution system, UV is not going to protect us because it has already done its job and it has no residual effect downstream. There's also some possibility of reactivation after long-term storage. So we do want to be careful if UV is our only form of disinfection, that we don't store the water for a extremely prolonged time, because there are some microorganisms that are able to repair their DNA. This would be primarily multi-strand DNA organisms that are able to do that. So just something to be aware of. So here's my analogy again of our exposure to sunshine as being somewhat equivalent to how we would look at dosage in a UV sterilizer. There are really two ingredients: the intensity of that light and how long we're exposed to it. So if you're fair-skinned as I am, I don't need to have high intensity in the sunlight outside if I have a long exposure time, if I'm out there all day long, to potentially get a sunburn. And that's because the overall dosage that I'm getting is still pretty high, even though it might be a cloudy day. Conversely, if I have very high intensity, I might not need very much exposure time at all to get a sunburn. And essentially, it is the same thing when we're inactivating microorganisms with a UV sterilizer. The 2 units of measure that we use to express our UV dosage are millijoules per centimeter squared, which is the more common measure today. And the other measure is microwatt seconds per centimeter squared. We don't see that actually used very often anymore, but if you do see it, the conversion factor is given there. 1 millijoule per centimeter squared is 1,000 microwatt seconds per centimeter squared. You may run into that second measure occasionally in some literature. So something else really important to understand is that exposure time, which is largely the flow rate of the water through the system, and UV intensity do not have equal effects on our dosage. The effect of flow rate or exposure time is almost perfectly linear. The only thing that makes it a little bit less than a linear relationship is there are differences in flow dynamics as water moves through the UV chamber at a low flow rate versus a high flow rate. Typically, there's a little bit less mixing at a low flow rate. Without perfect mixing, your linear relationship is lost very slightly. But from a general understanding point of view, think of it as if I reduce my flow rate by 50%, I will double my UV dose. UV intensity, though, has much more of an exponential relationship to dose. So very small increases or decreases in UV transmittance can cause a very significant increase or decrease in dose. So when we think about this, this is an area within our maintenance that we have a lot of control of. We can influence the UV transmittance through our system to help maintain the best possible dose that we can. Flow rate is largely dictated by the demands of our system, although we can add things like flow restrictors to control flow rate and have an influence on our dosage as well. So what kind of things affect intensity? Well, there's a few that are most critical for us to care about. The intensity of the UV lamp itself is really important. And there are varying degrees of effectiveness or intensity out of different lamps on the market. They are not all created equally. So there's different types of lamps, and I'll mention a few of those in a couple of minutes, but they can have an impact on the amount of UV output, as does the age. And even the water temperature or lamp operating temperature can play a role in how much UV intensity is put out as well. Lamps degrade over time, much like a fluorescent lamp tube will get dimmer and dimmer over its life. Fortunately, with the UV lamps, if you stay within the operating hours as recommended by the lamp manufacturers, you are usually very safe in terms of your lamp output. And the big tail off in lamp intensity would happen after that lamp hour recommendation from the manufacturer. So they can actually have a fairly slow, gradual decline within the lamp hours that are recommended by the manufacturer, but tail off quite dramatically after that. So we do want to make sure that lamps are replaced on schedule. In between the water and the UV lamp, you will always have some sort of UV sleeve. That sleeve is made out of quartz glass, and it can become fouled with sediments or iron deposits, hard water mineral deposits, etc. And so the clarity of that sleeve and how clean it is will play a role in the amount of UV intensity reaching the microorganisms in our water. So that's something else that we can pay attention to in our maintenance. And then the UV transmittance qualities of the water itself will play a role in how much UV light is transmitted through that water. So conveniently, we do have a test for that. And we do have test instruments that you can purchase if you want to maintain that. On the right-hand side of the screen there's a Realtek UVT tester there. That one's probably about $2,000 or thereabouts. There are less expensive options available as well. But there are things that can be contained within the water itself that can either block or absorb UV light. So sediment particles, for instance, can certainly block UV light directly, act like an umbrella effect. And organic matter, tannins and other natural organic compounds can absorb UV light and prevent it from reaching the contaminants in the water. So important to note on the latter part there is some of those organics can cause a tint or color change in the water. You know, tannins typically have a tea-like color that can be anything from very faint to very, very strong. And you know, that's kind of an obvious potential impact on our UV transmittance. However, it's possible to have water that is completely clear and still have organic matter in it that absorbs UV light. A good example of that would be if we were to dissolve sugar in water. Our UV transmittance would be very poor, but to our eyes, the water would look very, very clear. So you can't always rely on what the water looks like to know what its UV transmittance is. Certainly most water that is severely discolored, will generally have poor UV transmittance. So this chart just illustrates some of the common microorganisms that we see in water and the UV dose that we require to achieve a 3 and a 4 log inactivation. So 4 log means 99.99%, and that's reflected in the column on the right there. So for instance, for E. coli, at just a little under 6 millijoules per centimeter squared, we can achieve a 99.99% reduction. And you'll see the vast majority of the common organisms that we target are inactivated at a dose of less than 40 millijoules, which just so happens to be the dosage that most regulated or validated UV sterilizers are designed to produce as a bare minimum. So if the dosage was ever to drop below that level of 40 millijoules per centimeter squared, the system would be required to go into an alarm state. Now you can see down at the bottom, I also have listed most resistant adenovirus, which happens to have an inactivation dose for 4 log inactivation of 186 millijoules. So this is where we're getting into where our UV and chlorine work well together. So as we learned for crypto and giardia, UV is better than chlorine. For adenovirus, chlorine is better than UV. And this is one of the reasons why we use this dual barrier approach. But you can see that even fairly resistant viruses like rotavirus and poliovirus, Coxsackie B5 virus, etc., they're all inactivated at that dose of 40 millijoules to that 4 log level that we're targeting in our 43210 objective. So feed water quality, as I mentioned, is really important, and these guidelines will vary a little bit from manufacturer to manufacturer, but for the most part, these guidelines are pretty tried and true for most UV sterilizers on the market. First of all, we want to make sure we don't have any sediment particles that could cause that umbrella effect and block any UV transmittance. And for that reason, we want to filter down to not less than, to at least 5 microns. And we're actually pushing a lot of small water systems to go beyond that and filter down to 1 micron. At least 1 micron nominal, 1 micron absolute if they're on surface water sources. And that's just all aimed at ensuring there's no sediment particles that are going to block any of our UV light. Hardness, iron, and manganese can all cause fouling of our UV sleeve. So as iron and manganese oxidize, they will form a stain of minerals on that sleeve. As hardness precipitates into calcium carbonate or magnesium carbonate of the sleeve, that will also create a physical stain that will inhibit some of the UV light from reaching the water. So our guideline levels are generally 120 milligrams per liter for hardness, 0.3 milligrams per liter for iron, and 0.05 for manganese. Now those coincide with, or for the most part, with the normal aesthetic objectives that we target in our water supplies anyway, with the exception that the manganese standard, aesthetic standard, has now been reduced a little bit further to 0.02. Although we don't generally find that that is necessary for operation of the UV unit. 0.05 seems to be just fine with reasonable sleeve maintenance, which we'll talk about. Tannins and organics are not all created equally. They're relatively large classes of different molecules that all inhibit UV light to a different degree. So whereas our general rule says we want less than 4 milligrams per liter of total organic carbon, for certain types of organics, you would be able to exceed that. With others, you might be running into trouble a little bit lower. But that's a pretty good guideline that at 4 milligrams per liter, you're likely to start having some challenges. And interestingly enough, that 4 milligram per liter guideline is also a pretty good guideline for chlorination as to whether or not you're likely to have problems with the formation of disinfection byproducts. So we don't escape having to worry about organic precursors with UV either, because it can affect our UV transmittance. And as a general rule, we'd like to see our UV transmittance as a bare minimum of 75%. And I would strongly argue actually that we want it higher than that. We don't want to be operating on that 75% threshold, because most UV systems will have an alarm set point that will be triggered between about 68 and 75% UVT. So we don't want to operate on the edge of alarms. We want to be as far away from those alarms as possible. So before we can talk about maintenance and best practices, I just want to make sure you're familiar with some of the basic components of a system, so that when I'm mentioning the names of things, they make sense to you. So a UV sterilizer is actually a pretty simple piece of equipment. It'll usually consist of a stainless steel reaction chamber or reactor, which is just a fancy word for where the magic happens. This is where the actual sterilization occurs. So inside that sterilization chamber, there will be a UV lamp, and the UV lamp will be protected by a UV sleeve. In most systems, the water flows around the outside of this sleeve. The lamp is inside the sleeve, protected. There are a couple of products on the market where the reverse is true. The water flows through the sleeve and the light shines into the sleeve from the outside, so the reverse direction. Both of them have merits. Both of them really suffer from the same problem, which is sleeve fouling. There is some sort of ballast and controller. So there's a ballast that is usually able to auto-detect the line voltage so that it can maintain a very, very steady current and power to the UV lamp. And they have surprisingly large capabilities of handling voltage differences. So you can actually use the same UV controller on 110 volts as you use on 240 volts in many cases. On the controller, there will often be diagnostics or functional buttons that allow you to do things like mute alarms, reset lamp life counters. It may display the lamp hours or other information, UV intensity, etc., on a display. But the controllers vary quite a bit in terms of what information they provide and display to the user. As I mentioned, there's a lamp and sleeve, and there are different types of lamps. So one thing that I guess I'll address it now, but you'll see it come up in a future slide, is it is really, really important that you only use original equipment lamps in your UV system. And that is because a lamp may physically fit, but it might not be the same type of lamp as was previously present or specified by the manufacturer. So for instance, if you put a lamp in a UV Max Pro system from Trojan Technologies, that was a standard output lamp, it would only put out about 1/4 of the UV intensity of the amalgam lamp that normally goes with that system. So it's very important that you use the correct lamp to ensure that your validation is still valid. Your electrical safety certifications are valid, and we've seen actually a fair bit of evidence in some of the non-genuine lamps on the market that they do not have the same life. They do not have the same coatings on them for UV transmissivity. So you are not assured of the same level of dosage. And in extreme cases, we've even seen situations where the lamp pins don't fit properly. They're a little loose. They cause arcing, and have actually had melted lamp harnesses and even ballast and controller damage. So it's not something that you want to take any chances with. I know it's tempting from a cost perspective to save a few dollars using a knockoff lamp, but technically speaking, it avoids your certifications on the product, and you may not be getting the protection that you're expecting. On the side of the UV chamber, most of the time you're going to find a UV intensity monitor. So on the left-hand side, about halfway up this chamber, you see a little black device. That is the intensity monitor. So it has a little window with a photovoltaic cell that is excited by UV light. When it's excited by UV light, it creates electricity. That electricity can be measured by the controller to know the intensity of the UV light that's reaching the outermost part of that UV chamber. They're expensive little devices, and they are considered a wear and tear item. So just like your lamp and sleeve, they don't last forever, but typical lifespans are kind of in the 4 to 5 years for the intensity monitors. Remember, they're exposed to UV light at high intensity 24 hours a day, so they do they do have a life. They do wear out. So some other common features and accessories, when we're talking about validated product, we're usually talking for small water systems about NSF standard 55 class A. That's very important to be distinguished against NSF 55 class B. The class A devices have the 40 millijoule per centimeter squared minimum UV dose. A class B device is really designed for retreating water that was already treated to a municipal standard. And it only has a dosage of 16 millijoules per centimeter squared, and it's also not required to have some of the additional safety and monitoring systems, such as UV intensity monitors, etc., that are found in the Class A devices. Whenever you go over 30 gallons per minute, the NSF 55 Class A standard has no protocol for testing beyond 30 gallons per minute. So when you get up into that range, you will see devices certified under the US EPA UV disinfection guidance manual. And that validation does not have that flow rate limitation. Now, it's very, very common if you have an application that's beyond 30 gallons per minute, you may have multiple NSF 55 Class A units as opposed to one larger US EPA validated unit. And I would actually argue in most cases that that would be preferred for a number of reasons. You get some additional redundancy. You know, if one unit is down, at least have some water being treated. And quite honestly, multiple NSF 55 Class A units are often cheaper than one larger US EPA validated unit. Just be aware that for your applications, if you're providing water to a public setting, validation is required to get a construction permit from the health authority. So there are lots of UV models on the market that are not third-party validated. Unfortunately, those are not applications those are not units that you can consider for your applications. Some other accessories, most of the time the health authority will require that the UV unit be equipped with an emergency solenoid shutoff valve. That valve is designed to close and prevent water flow if there's ever an alarm condition. An alarm condition can occur if the UV transmittance drops too low, such that a safe dose can no longer be maintained, or if the lamp burns out, or if there's a power failure. Obviously, if there's a power failure, the UV light is not going to be operational and it's not disinfecting the water, so that solenoid will close. There's usually an internal or external flow restrictor that restricts the flow rate of the water to whatever the regulated or validated capacity of that system is. There are sometimes cooling systems like thermal valves or fans The system on the prior page there on the top right, this one has a cooling fan built in there. That's becoming a more popular feature these days. There are data collection and logging systems. There are also now some systems available for remote monitoring as well that are becoming quite affordable, that use Wi-Fi so that you can access the system and receive alerts by phone or by text. And there's a couple of models now on the market that are doing what we refer to as true dose monitoring. Most of the monitoring historically has just been related to monitoring UV intensity, with the assumption in calculating the dosage level that they're always running at full capacity. And we all know that we don't always run our systems at full capacity. So by adding flow meters to the UV sterilizers, we can actually calculate the true dose based on the current intensity and our actual flow rate. And that can be very, very handy as a technology for us. So some best practices considerations. Technically speaking, because you have electricity and water nearby, you should be using a GFCI outlet or an outlet protected by a GFCI breaker. It's a good idea to have, as a bare minimum, a surge protector on the system to help protect against power surges that could potentially damage the equipment. This is a problem we see in a lot of coastal areas that deal with a lot of high wind and windstorms causing power failures and spikes that can potentially damage the UV controllers. A power backup, like an uninterruptible power supply you would use on a personal computer, is a great way to provide both surge protection and some backup power for short outages. Chamber and sensor orientation matters. So generally speaking, for most UV sterilizers, they should be installed vertically rather than horizontally. And the chamber orientation, if it is permitted to be horizontally, there can be some problems associated with the sensor being either on the top or the bottom of the chamber. On the top, it'll tend to pick up air bubbles that will interfere with the sensor reading, and on the bottom, it can be an area where sediments and debris tend to settle. So in most cases, chambers should be horizontal. Pay attention to the manufacturer's guidelines there. We want lots of sample ports, shutoffs, and an opportunity to drain the system for maintenance. That's probably one of the things I see done least often. Ideally at the low point on the inlet of the UV sterilizer, if you can put a ball valve just where you can, a sample port or a drainage port where you can drain the UV chamber, it really helps for doing quick maintenance. Most regulations from the health authorities prohibit a bypass. It is something that can be allowed under certain circumstances if pre-arranged with your drinking water officer, but generally speaking, UV bypasses are not permitted. The location of various components are important as well. Solenoids ideally should be located as close to the unit as possible, and preferably before the first corner. Generally speaking, we like to see solenoids right on the outlet of the UV sterilizer. We don't want to have long lengths of pipe, and particularly around corners and such, where microorganisms might be able to swim past the UV chamber into that downstream line before it reaches the physical barrier of the solenoid. Microorganisms, given enough time and a long power outage, can definitely move around in the pipe there. Keep electronics out of areas where they're going to get wet. That seems obvious, but is very often not followed. Use good plumbing materials. Ensure that any materials that may be exposed to UV light on the inlet and outlet are resistant. This is an area where we often see stainless steel used to get around the first corner, or even copper before you go to PVC or PEX and such. And make sure that there's lots of room for maintenance. And don't forget the fact that the lamp needs to come out the top of the chamber. So don't mount the chamber right to the ceiling, or you're not going to be able to get your lamp out. So here's an example of a fairly simple UV installation. You can see the solenoid valve, which is the black component, immediately below the black controller on the left, is immediately located on the outlet of the UV chamber. We can see the chamber is installed vertically. The electronics are up nice and high where they're less likely to be sprayed by water, etc. And if you have a UV system with a flow meter, it's very important that you have a non-turbulent flow. So down on the bottom on right of the UV chamber, you'll see a black device. That's actually a flow meter in this case. We have a nice straight length of pipe going into that flow meter so that we have laminar flow so that flow meter can read accurately. If we were to have an elbow immediately before that flow meter, it might not read very accurately, and it might interfere with our dosage monitoring. So best practices. Most important thing that you can do for your UV system, other than ensuring that all of your pre-treatment equipment is all operating correctly, so if you have iron filters or water softeners, that those are all kept operating properly, is to ensure that your quartz sleeve and your UV sensor window are cleaned regularly. And this will be a function, as I said earlier, of your own water conditions. If you don't have iron or manganese or hardness in your water, you very likely will not have to clean it nearly as often as a system that does, especially if a system has those things and is not pre-treating adequately for them. To clean the sleeve, it needs to be removed from the system. The recommended cleaner by most manufacturers is CLR. I'm sure you've seen their annoying commercials on TV. It is a very good product. A lot of systems like to have extra sleeves on hand, so they pop the sleeve out to clean it. They put their reserve sleeve back in immediately, and then they will soak the sleeve that they've just taken out in the CLR for a little while. Wipe it down with a soft cotton cloth. Ideally, a white cloth is recommended so you can get a visual take on what you cleaned off. It's good feedback to, how dirty was it. Sometimes it looks pretty clean to our eyes until we wipe it across a white cloth and we see the discoloration that we removed. The little sensor windows need to be cleaned as well. They have a quartz glass window, and you just unscrew the sensor from the side of the chamber, use a Q-tip with some CLR on it, or you can even get a little thimble or a little tiny cup and soak the end of the sensor window in the CLR for up to half an hour to break up stubborn deposits if they're there. Rinse both the sleeve and the sensor window off with nice clean water before putting it back into service. And a couple of other really important points: absolutely never use glass cleaners like Windex on your sleeves. They contain organics that will leave a residue that absorbs UV light. It'll look really clean visually to your eye, but not to the UV light. Don't handle the lamps and sleeves with bare hands. Wear gloves. Don't use powdered rubber gloves. They tend to leave a residue behind as well. And don't use any lubricants on the sleeve O-rings. It can be very tempting because it would certainly make everything assemble easier when you put things back together, but that lubricant will get on the sleeve, I guarantee it, and will, again, because it contains organics, it'll absorb UV light and cause you a lot more harm than good. Sleeves should always be replaced if there's any etching or clouding that cannot be removed by fairly simple cleaning. And the vast majority of manufacturers are actually recommending now to just replace your sleeves every few years. And many of them are even providing lamp sleeve combos where you buy the lamp and sleeve together, you're getting the sleeve for next to nothing. They're really trying to encourage that because they know it results in better UV transmittance. So follow the manufacturer's recommended schedule for lamp replacements. Most of them on the market need to be replaced every year, or 9,000 lamp hours. There are a few models like the UV Max Pro from Trojan that use amalgam lamps that have a 2-year lamp life. Just be sure that you're following the manufacturer's schedule. Technically speaking, after you replace lamps, you should be disinfecting the downstream system. Now this will depend on the, how extensive your distribution network is after your UV sterilizer and whether or not you're already using chlorination. But disinfecting the chamber and any equipment between the UV and your chlorination system is a good thing to do every time you replace a lamp. And as I said earlier, only use lamps designed specifically for your system. Keep a logbook documenting all of your maintenance. It is so useful if you ever need to go back and make reference to what happened when. And certainly also keep a logbook of any alarm conditions, what you did to resolve them, what you discovered during any troubleshooting. So now we're going to talk a little bit about troubleshooting here. And then we'll have some time for some questions before I head into chlorination. So some general troubleshooting suggestions. Number one, don't assume anything. This is actually probably one of the biggest frustrations that we run into is people make an assumption right off the bat that some piece of equipment has failed and that's why they're getting an alarm. It's actually much more common for the problem to be associated with a maintenance issue like a dirty sleeve or a water quality issue. Something has changed whereby maybe your pretreatment isn't working as well or your source water conditions have changed such that the UV transmittance has dropped. So don't make any assumptions off the start. Just follow the troubleshooting procedures and let them lead you to an answer. Take spare parts with you to the site or have them on site, ideally, all the time so that you're not left without critical parts that you might need. And as a bare minimum, I would suggest that that means a lamp and sleeve for each UV sterilizer that you have. And it wouldn't be a bad idea in most cases to have a spare UV intensity monitor. If you have a UV T tester, it's very, very handy to monitor changes in your source water quality. And I would certainly recommend it for systems that are plagued by organic problems that might be either seasonal or related to events like rainfall, etc. You need to know what's happening and what kind of fluctuations you're seeing in your source water UVT. It's important to consider the timing of alarms. For instance, did you perform recent maintenance that might have actually caused a problem? Are there problems associated with maybe regeneration of a water softener or other piece of equipment, i.e. an alarm the morning after a softener regenerates, and it happens over and over. That can be very diagnostic to look back at the times. And if you're not logging them in a book, it's very easy to forget exactly when those events happened. Consider environmental conditions like air temperature and humidity. Very cold air temperature will affect UV lamp output. So that could be the cause of a UV alarm. Conversely, if you have sun shining in a window right on your UV chamber and heating it up, excessive heat can also be problematic. So consider those sorts of conditions. If you're going to request assistance from the manufacturer or your supplier, make sure that you leave the site with serial numbers and ideally a water sample in case they want it for testing. And again, document everything you do and do one thing at a time. In troubleshooting, one of the frustrations that we deal with is someone will do 5 things to the system and they'll get it operating, and then the same problem will come up and they won't know which of the 5 things solved the problem. So then they got to do all 5 things again instead of the one true thing that solved the problem. So doing things one at a time, very methodical, helps tremendously. So a couple of problems that can come up, lamp failure, definitely consider the age of the lamp, inspect the lamp for physical damage. Sometimes it'll be very obvious as to why the lamp has failed. This is where having a spare on hand can definitely help because it's an easy thing to test. Just be aware that sometimes you will have a low UV intensity problem that is, you replace the lamp and you think, oh, it solved the problem, therefore I had a bad lamp. That might not necessarily be the case. You might just have put a lamp in that had more intensity than the one that you took out, and it pushed you just above the alarm threshold that was being caused by something else, like poor UV transmittance or a dirty sleeve or something like that. So don't just immediately jump to lamp failure if you have an intensity type alarm. If you have a lamp failure type alarm, certainly look to a lamp as being a cause. But if it's an intensity related alarm, lamp would certainly not be the first thing on your list. Some of the other causes of a lamp failure alarm would be that the lamp is not actually firing at all. So that could be caused by a ballast failure, a power supply problem. Sometimes we've seen cases where the electrical outlet that the unit's plugged into is no longer getting power because a breaker has failed, or the uninterruptible power supply has failed. Some of the units have fuses in them, so if you plug it in and no lights come on, it could be a fuse related issue. And then some systems have safety switches that are designed to engage only when the lamp is plugged into the lamp harness in the correct chamber. And that's there so nobody can plug a lamp into a lamp harness and fire it up outside of the chamber where someone's eyes might be exposed to the UV light, which would be dangerous to their eyesight. So sometimes these little safety switches can fail, or they haven't been engaged properly. The lamp harness is not correctly connected. So UV intensity alarms are probably the #1 alarm related problem that we get questions about. So first off, make sure that the sensor wasn't actually unplugged from the controller accidentally. If it was, before you plug it in, you should power the system off, plug it in, and then power the system back up. Most of the systems out there need to see that it is connected at boot up. So sometimes just plugging it back in will not remedy that type of problem, especially if it had been booted with the sensor unplugged. I have this bolded for a reason. Clean the UV sensor window And honestly, if you still have an alarm problem, clean it again. Be really, really sure that you've got the sensor and the sleeve clean before you move on to any other testing. Thereafter, the most important test that you can do, we refer to as a dry test. So you would drain the water out of the chamber. That's where having that drain port is handy. And you would fire up the system with no water in it. If it passes that test, the problem is probably your feed water quality, and it is not related to any physical equipment on the UV sterilizer. If it fails the dry test and is still in alarm, the first thing that we would suspect, assuming that we've done a good job of cleaning the sleeve and sensor window, is the lamp. And we should have a spare lamp on the shelf, right? So we would replace the lamp next. And if that still fails, we would consider doing a dry test again with the new lamp. And then if that fails, we would start considering a possibility that we have a bad UV intensity sensor or controller. And I can tell you that those instances are really uncommon. We do not see that very often. It's usually going to be a water quality issue or lamp related. And the lamp cases are actually quite unusual too. They're not very common. So when it comes to the water quality, you may want to ask yourself whether or not conditions may have changed because of freshet, heavy rain, has my pretreatment failed, those sorts of questions. I wish I had more time to spend on this because this is a common area of problems and frustrations. So if you have any individual circumstances that you'd like to go over, you can certainly contact me in the next couple of weeks and I'd be happy to discuss them with you. Ballast failure, super rare, usually is kind of a default diagnosis after all other items have been addressed. If ballast failures are happening commonly in your system, one of the things that you may want to consider doing is putting in some surge protection, because usually that's related to a power related problem, surges or brownouts, inconsistent power, that sort of thing. Okay, one last thing. If you have a site that has multiple UV units installed in parallel, and all of the systems or multiple systems are all reacting the same way, you should really suspect strongly that it's a water quality related problem. It's not likely you have 3 lamps all failing at the same time. And if only one unit is in alarm, one of the nice things about having a redundant system like that is, even if you don't have spare parts on the shelf, you have spare parts on the other unit. So you can swap one part at a time and see if the problem follows over to the other unit. So if you swap lamps and the problem moves from unit A to unit B, you have a pretty strong suspect there that the lamp is the underlying problem. And you can do the same thing with intensity monitors, controllers, and other parts as well. Okay, so let's see if we can handle a couple of questions here. I see one here. We spoke last year regarding issues with my UV system. UV wattage.
Grant, I'm just gonna pop in for a second
Sure.
to remind you that there's only 20 minutes left.
Okay, so why don't we have people send in their questions related to UV then, and I can certainly cover them off individually. And
Sure.
maybe we can also gather up all of those questions, put all of the answers together and share them with everybody, so you can read about other people's problems and solutions as well.
Sure, and I don't know. I was just going to say, I'm not sure what happens after our 90 minutes. If you want to try and go past the deadline, um,
Okay.
there's a there's a chance we'll get cut off. So I just wanted to put that out there. And I'm just going to ask quickly, can we, I guess, share your Home Plus email with
Yes,
people
of
so they
course.
can is that okay? Okay.
Yes,
Go
absolutely.
ahead. Sorry.
Okay, well, I'll move on then in the interest of time here. And sorry, like I said, we usually cover this in a much longer session, so I'll do my best to run through chlorination quickly here. So as mentioned, advantages of chlorine, effectiveness against some of the more resistant viruses, and we also now get our residual treatment all the way through to the ends of our distribution, which is something that UV cannot offer for us. Disadvantages, it's a little more complicated to operate. We're going to be handling some chemicals. There are some negative public perceptions of chemicals and taste and odor, and we can help you deal with some of those things, of course. We do have the potential for formation of disinfection byproducts when organics are present, so we have to monitor and be careful about that. And sometimes our contact time requirements can be a little troublesome to meet, especially in small systems where space might be a high priority or not available for us. So what is a typical chlorination system composed of? And I'm speaking here just of small water systems. So in municipal systems, we'll see other types of equipment where chlorine can be used in a gas form instead of a liquid form, and it may even be generated on site. Won't be dealing with that, unfortunately, today. So the chemical feed pump is the actual pump that injects the chlorine. It'll usually either be peristaltic or a diaphragm pump. A peristaltic pump usually has a little tube that gets squeezed by a roller, and it simply pushes the chemical into the line. And a diaphragm metering pump actually sounds like it's pulsing, and it's actually squeezing a little diaphragm to inject the solution into the line. We have something called an injection point or quill. That's the actual point where the chlorine is injected into your water line. And that injection point will have a check valve in it usually, or a check valve associated with it, to prevent pressurized water from your system from flowing backwards through the chlorination system. If there is ever a pressure differential that allowed for that to occur, that little check valve would prevent it. There's a solution tank that holds your chlorine solution. Often that'll have some sort of spill containment around it. We have a foot valve inside the solution tank. That's the point at which the chlorine is actually sucked up. It'll usually have a little screen on it to keep debris from getting sucked in there as well. It'll be lifted a few inches off the bottom of the solution tank, again, to prevent sucking debris off the bottom of the tank. And it will also have a check valve in it to ensure that your pump does not lose prime when it stops pumping. And you may even have a little level switch or alert on there that if the solution level drops below your foot valve, you'll get some sort of alarm notification. You may have probes and analyzers. So some of the more sophisticated systems out there in larger community systems will have a chlorine analyzer that is actually monitoring the chlorine levels in parts per million. Most small and micro systems don't have that because of the relatively high cost of those analyzers. You may also have a flow meter that controls or measures the flow rate of the water so it can control the injection rate of the chlorine proportional to that flow rate. So when your flow rate goes up, it injects more chlorine. Flow rate goes down, it injects less. And that can be done a few different ways, but it's typically a pulse flow meter. You'll have some sort of water storage, which provides our retention time for contact. And you may have some sort of device, either static or active, to provide mixing. and you should have some safety equipment around, certainly PPE, and in many cases an eye wash station. So this diagram shows a really simple small water system, chlorine injection system. So we have a pulse flow meter in this case controlling an injection pump, which is sitting on top of a solution tank. At the bottom of the solution tank, we have our little foot valve, and can't really see it there, but we have an injection point kind of injecting into the line. We have a static mixer following that. Not every system will have that, but a static mixer just tries to create some turbulent flow and mixing of the chlorine with the raw water. And then in this case, the water flows into a couple of baffle tanks for our contact. We have a flow restrictor, that's the FR there. That's restricting the flow through our system to a particular level to achieve our desired contact time, and we have a couple of sample ports in different locations. Contact time can be provided by many, many different options. So on the previous screen, I showed a couple of baffle tanks in series, but this could be a holding tank, a reservoir. It could be just coiled pipe buried in the ground. It could be a large diameter section of pipe buried in the ground as well. Could even be the distribution pipe. If you have, a kilometer of pipe before the first home on your distribution system, you can use that for contact time. And it could even be potentially other treatment equipment, although that's pretty uncommon. But there's a whole bunch of things that can qualify as a contact vessel for our contact time. Basically, anything that holds water between the chlorine injection point, or maybe best defined where it's achieved at least some level of mixing, and your first point of use on your distribution network. Anywhere in between, we can achieve contact time. So contact time is, we refer to as, or what we're trying to achieve is CT, concentration times time. So kind of like with UV, we have concentration, think of that as intensity, and time being our exposure time or flow rate. It's very much the same. So our CT is kind of like our dosage, and we just need to ensure that the dosage required is less than the dosage that we're actually achieving. And we can calculate our CT value for each and every component in which water is stored. So we could have a reservoir, we could have a reservoir and 2 baffle tanks, and then 100 feet of 4-inch pipe, or we have a whole bunch of different things. But we take the CT value from each of those, add them together to get our total CT. And the big question is, well, how much CT do we actually need? Well, the answer is that it depends. We have to consider both water temperature and pH. Now, normally in BC, we tend to use a CT of 10.7, which is kind of like saying we have 1 part per million of chlorine for 10.7 minutes. And that would be suitable for 4-log inactivation of adenovirus at a pH range of 6 to 9 at a water temperature of 2 degrees Celsius. If the water's warmer than that, technically we need less CT. If the pH is outside of that range, then we need to break out our EPA guidance manual for disinfection profiling and benchmarking and look up what the CT value is for our pH range of our system. But 6 to 9 tends to work pretty well for most applications in BC, and assuming a cold water temperature of 2 degrees Celsius is kind of worst case scenario. So a few things to know about chlorine effectiveness. We should be measuring our chlorine concentration at the outlet of the storage. So it's at the last point in time where we are using that contact for the purposes of our CT calculation. This also has to be matched, though, with the fact that we need residual at the end of our line. And generally, we're looking for a minimum of 0.2 free chlorine at the very end of our distribution system. So sometimes we'll have to aim quite a bit higher than what we normally would want to do at the end of our contact vessels or storage in order to get that residual as high as we need it at the end of the distribution. The more extensive your distribution is, the more challenging that becomes. And of course, the trade-off is that if we increase the chlorine concentration too much, we will negatively impact taste and odor. So common values that we tend to see, somewhere between 0.4 and 1 part per million at the outlet of contact tanks is generally ideal to strike a balance between having to have bigger contact vessels and, so keeping the contact vessel sizes small versus impacting the taste and odor of the water for our consumers. So there's always that trade-off. If we increase chlorine concentration, we reduce the amount of contact time and therefore the size of the contact vessels we need, but we do that with an implication on taste and odor. So calculating it is fairly straightforward. We take our chlorine concentration, we multiply that by what we refer to as a short-circuiting factor, which I'll talk about in a second. We multiply that by the minimum water volume that we have in our storage vessel. And there are tools for calculating, for instance, how much water does 100 feet of 4-inch pipe hold? You can calculate those things. And it's important that it says minimum water volume there because we need to take into account the fact that our reservoirs are not always full and we got to base things on worst case scenario. So that's usually the level at which your tank starts refilling itself upon drawdown. And then we divide that by the maximum outlet flow rate from that reservoir to get the CT for that particular device. Now, the short-circuiting factor recognizes that not all types of tanks and so on have equal contact time. Some have short-circuiting built in, and I'm going to show you some quick examples. So, sorry about the blurriness of this picture, but you can see in this little reservoir here that the inlet and outlet are located fairly close to each other, and the arrows depict a path of least resistance that some of the water is going to take. So even though that reservoir, say, may hold 1,000 gallons, we will only get credit for it in our CT calculation of probably somewhere between 5 and 10% of that value because water is shortcutting. So the short-circuiting factor is trying to take into account the fact that not all water is going to have a long exposure time in that particular reservoir. So we can improve the design of this reservoir by doing something like this, where the water is sprayed in evenly on top and collected down at the bottom. This will provide overall better mixing and an average contact time that is longer. And as you can imagine, it can get quite subjective, and this is where you'll have to work with your drinking water officer and public health engineer if you're looking at ever trying to influence your short-circuiting factor to try and find ways to design it better. They will need to be involved because of the subjectivity of this. In some cases, you can buy baffle tanks where studies have already been done and they will provide the baffle factor for you. So for instance, this particular tank right here has a baffle factor of 0.6, which is actually really high, 60%. And that's been tested and by the manufacturer, third-party endorsed and accepted by the health authorities. But when you're talking about reservoirs, it can be a little more subjective. Here's a much better example. Now we've actually added baffles inside our reservoir. The water has to take a really tortuous path. So now our short circuiting factor is improving. And in a piece of long pipe, long skinny pipe, your short circuiting factor is basically 100% in the sense that zero water is able to bypass. It has to follow a long tortuous path no matter what. Just wanted to illustrate this one example. This is a typical pressure tank. The inlet and outlet are the same. It has absolutely no value for your contact time. The short circuiting factor is 0%. So some important things to know about the chlorine that we're injecting itself. Of course, it's actually sodium hypochlorite. It ranges typically from 6 to 12%, although there are other variations on the market. Make sure it's NSF validated. You're injecting something into potable water, it needs to be certified as being appropriate for potable water. We shouldn't be using industrial products here that may have impurities. Make sure your chlorine is fresh, and I can't emphasize this enough. Chlorine sitting on the shelf, even though the bottle may never have been opened, degrades over time. Common values for bottles that have been opened is that it'll be about half the strength that it started at in 6 months. So if you're trying to be accurate about how you're injecting your chlorine, you're best to mix small batches and do it frequently. So we try and stay with under 1 month supply at a time in your solution tank. We also recommend in general diluting it heavily. This will allow you to achieve much more even dosing. So if you're injecting a strong concentration of chlorine, your injection pump might run and then stop and have a pause that could be 30 seconds, a minute long, then inject again, then have a big long pause, then inject again. Well, every time it pauses, you have a slug of unchlorinated water going through. Every time it injects, you have a very, very strongly chlorinated slug of water going through. It provides very, very poor mixing. You're far better to inject faster, but at a weaker solution, it'll achieve a much more even, steady, consistent result. And when you're doing your dilution, use clean water, especially water that has high levels of iron, manganese, hardness, or organics can be problematic. Hard water deposits will cause fouling of the screen on your foot valve. Iron and manganese will cause precipitates that will build up in the solution tank. And organics have chlorine demand and can form disinfection byproducts. So we want to avoid all of those things. Use nice clean water to mix or dilute your chlorine. So some important things about maintenance. And if we lose you here, I really apologize, guys. I will make sure the presentation's available for you and you can follow the last few slides. Follow safety precautions. We're using harmful chemicals here. Wear the appropriate protection, ventilate properly, etc. Again, always ensure your chlorine solution is fresh. Clean and inspect your injection points, foot valves, and check valves that are contained within those regularly. They're probably the most common point of failure, and they're easily cleaned and inspected or even replaced. They're not very expensive. In the peristaltic metering pumps, replace the peristaltic tubes regularly. Keep spare ones on hand for sure. And of course, monitor your chlorine residuals and keep a logbook that you can refer back to. Common problems. A low chlorine residual is probably one of the most common problems that we hear about. So this can occur when you've had a sudden increase in chlorine demand in your system due to feed water changes, particularly if iron, manganese, or organics levels spike. So we see that this time of year with turbidity levels and organics levels increasing due to freshet and certainly the amount of rain we've had lately as well. Your chlorine could simply be getting old. You know, if you haven't replaced your batch and you're starting to suffer from low residuals, you may be able to turn your pump up temporarily to compensate, but if you've kind of reached your max settings, it could just be you need some new solution. Sometimes you'll have a situation where your pump capacity cannot keep up with higher flow rates that might be happening from time to time. So if you've had increased demands on your system, particularly related to flow rate, you can watch for this problem by listening to see if your port and watching to see if your pump continues to pump once your water flow has stopped. Essentially what that means is your pump has fallen behind where it wants to be or where it thinks it needs to be and where it probably does need to be to keep up with your flow rate. So you'll get, the pump will continue trying to pump to catch up with that flow rate where it fell behind after the water shuts off. It's a really strong sign that your pump capacity is not keeping up. If that's the case, your dilution rate might be too strong and you'd be better to go back to a slightly stronger solution with less dilution. We can also have times where chlorine residual drops low because of seasonal factors related to having too much contact time. So we think of this in recreational properties, for instance, where water demand is much, much lower in the winter months than in the summer months. And in the winter, sometimes there might only be a caretaker on site, but the reservoir is still holding the same amount of water. So the reservoir turnover becomes very, very low, and we have chlorine loss just through dissipation into the air. In these cases, you can either adjust your storage levels seasonally to compensate for that sort of thing, or you can put a secondary chlorine recirculation loop on your reservoir with a secondary chlorine, a secondary chlorine pump that tops up the chlorine anytime it's running low in the reservoir. That's a very common problem in BC because we have a lot of recreational type properties. You may also have an injection point or foot valve that, or tubing that is getting clogged up and restricting the amount of chlorine that the pump is able to inject into the line. So it's something you can certainly pay attention to as well. You may also have a problem where chlorine's not always low, but it's fluctuating. You're having a really hard time dialing into a steady level. So some of the things to pay attention to there would be, you know, is the problem related to fluctuations in the feed water quality? So there are various things that can be in the water that the chlorine reacts with and gets used up. And that chlorine is no longer available to be part of our chlorine residual. So we have our total chlorine that we inject into the line minus our chlorine demand equals our chlorine residual. So organics and iron and manganese are kind of our big chlorine demands usually. And if they're fluctuating, but we're injecting a steady amount of chlorine into the line, our chlorine residual will also fluctuate. So if that's the problem, we may be able to take some source protection measures that reduce the impacts of some of those things that are leading to fluctuating chlorine demand. Might be able to reduce turbidity getting into the system, for instance. But more than likely, this is where we would want to start looking at increasing the level of pre-treatment in our system to address some of those issues that are causing the chlorine demand fluctuations. So maybe we'd be putting in treatment for iron or putting in treatment for organics. Organics treatment could also help ward off some of the organics that would lead to disinfection byproduct formation as well. So that's something that we should consider if we have fluctuations. Is the fluctuation caused by faulty equipment, or is it just caused by fluctuating chlorine demand in our source water? If we do have a chlorine analyzer, make sure the probes and sensors are cleaned and calibrated. The manufacturer of those analyzers will have guidelines for that can be followed. And that calibration can be quite important to be done on a regular basis. As we mentioned earlier, are you diluting enough? This is something more often that we would see in a small system at startup, where they're injecting a solution that's too strong, and they have very, very long pauses between their injections. So when they're actually trying to measure the residual coming out of the system, the pauses are so long that in their contact vessels, they're not even getting any mixing, or not enough mixing to result in a nice steady level of chlorination. So the solutions there would be to improve mixing and very, very likely to increase dilution. Again, similar thing could happen if our pump capacity falls behind. So if we have periods where we have periodic high flow and the injection pump can't keep up to that high flow, i.e. it's undersized or undersized relative to the level of dilution that we're doing, we could fall short of our chlorine objectives during high flows, but we might meet our objectives just fine when the water's flowing at a lower pace. So we should give some consideration to whether or not our fluctuation in residuals is caused by the pump not keeping up some of the time. We can fix that by changing our dilution, installing a pump with a higher capacity. And in the name of a peristaltic pump, that may be as simple as just installing a peristaltic tube with a bigger diameter and a bigger diameter roller to accommodate that. You might not have to replace the whole pump. We could also be having a problem with dissipation if we have big fluctuations in water demand off our system as well. So if we have maybe high demand on the weekends, but low demand during the week, we might be getting dissipation during the week, and then everything might be fine on the weekends. And we could fix a problem like that by, again, having a secondary injection on a loop going into our reservoir that just tops up the chlorine as necessary. So that's a very, very common problem that we deal with. So last few common problems that I'll hit on is loss of prime. So this happens when the pump is unable to pump because the air has got into the system. So that can happen if the solution tank runs empty and we start sucking air into the system. So obviously our maintenance in keeping our solution tank topped up is important there. You could have a failure of the foot valve that allows chlorine solution to drain out of the tubing when the pump shuts off. So that's an opportunity to clean the screen at the bottom, inspect the check valve that's built into the foot valve there, and make sure it's operating correctly. And you could be getting a lot of off-gassing, and off-gassing in chlorine systems tends to happen when we inject higher concentration solutions. So we may be able to consider, depending on the capacity of our pump, we may be able to consider diluting more to reduce the off-gassing problem, and even reducing the tubing length can help reduce the off-gassing effect. Most of the peristaltic pumps will reprime themselves. So if this is a really big problem for you and you have a diaphragm pump, you could consider switching potentially to a peristaltic style pump. If it loses prime, usually it will get prime back automatically for you. If you're having problems with disinfection byproduct formation, Most of the time, what you're going to have to do to solve this problem is look at removing the organic precursors. So you're going to be pre-treating to remove the organics. That would be beneficial to taste and odor. It would be beneficial for UV dose, and it would be beneficial for chlorine consistency and eliminating the disinfection byproduct formation. Granted, removing organics is not always easy or practical in a lot of small systems, but it is something that should be considered. And as another option, and this is more common in larger systems than small and micro systems, but you can consider injecting chloramine instead of chlorine. Chloramine is a combination of chlorine and ammonia. And it tends to reduce the disinfection byproduct formation. And it is certainly an option that a lot of larger municipalities and community systems look at. Another problem you may deal with is complaints about taste and odor. And this can often occur as a result of our residuals being too high. And this is not uncommon in a situation where we attempt to compensate for our fluctuating chlorine demand. So we actually have this problem here. We have difficulty to maintain steady residuals. So what we do is we compensate that by just simply upping the chlorine that we're injecting. And at some point that comes with the consequence of affecting taste and odor. And we have some guidelines as well as to maximum chlorine levels that we want to inject, and this often happens out of an honest attempt to solve other problems. One of those other problems can be a case where you have a long and extensive distribution network, and in order to get that 0.2 residual at the end of your distribution line, the first few houses on the line have to get 2 or 3 parts per million. That is a very big challenge to deal with. Some of that can come in the long term through infrastructure replacement, pipe replacement, especially if you have old cement asbestos lines that might have years and years of mineral buildup in them and so on. Replacing that with modern pipe in better condition might make it easier to get the residual out to the end of the line. But it may also mean that you have to consider having a chlorine booster station somewhere else along the line, where you don't have to inject so much up front, but to maintain the residual at the end, you give it a little boost partway along the line. Those are big challenges. They're often costly. They're often hard to make the decision as to the best solution. But that's certainly a common problem that you will encounter. Improving the pre-treatment to reduce some of the organic precursors to chlorine demand can sometimes help with this problem as well. But this is one where probably talking to a consultant is most likely to help you zero in on the best solution for your problem. Okay, so I think we've gone, unfortunately, well over our time. I really, really appreciate you hanging in there a little bit longer with us, and I see that most of you were able to hang in there, so I really, really appreciate it. If you're interested, I can hang on the line for a little while to answer a few questions, and I'll certainly get all of the questions from Natasha and Mike and make sure they're followed up on. They will provide my contact information so you can reach out to me directly if you have any questions specific to your system or you want any additional details on the things that we talked about today.
Thanks so much, Grant. That was great. I think the fact that so many people are still here shows how interesting and informative that talk has been. Um, I will go through a few questions verbally because sometimes it's easier. So if people want to hang in there, I am having a bit of a technical problem myself where I'm not able to copy and paste the questions into chat, but I will be able to verbalize them now so we can discuss, and I will do a follow-up and I'll send out a Q&A after. We did have a question that came in very early from John Weeb. He asks, when using the DPD chlorine test, I suspect the manganese content of the water may be affecting the resulting readings. How can I be sure this is the case? And if it is, how do I best correct for the manganese?
That's a great question, and you are right to suspect that manganese can cause some interference with the DPD chlorine tests. I think the best way to determine if that's having a problem would be to mitigate the problem and do two parallel tests and compare the results. There are a couple of different chemical additives that can be added to the test to negate the effect of manganese, one of which is potassium iodide. And the other one, I think, is some form of arsenic, so you probably want to stay away from that one. If you were to reach out to your test kit supplier, many of them have a specific protocol for their specific test kit for this mitigation. I know a lot of you probably use the Hawk brand of test kits, and they have a very specific procedure. I believe that procedure is even listed on their website. So if you're to do like a Hack DPD manganese potassium iodide search, I'm sure it would come up. And I would say that that procedure, though, is unfortunately going to be very likely dependent on the test kit that you're using. So I don't know if I could give you a test procedure that would work, add X number of drops of potassium iodide and it'll work with all test instruments. I think it's going to be very specific to individual instruments. But potassium iodide, which is not too hard to come by, should be the material that you'll probably be using to do that.
Awesome, thank you. Cooper Husband had a question. Is it better to place the UV solenoid valve directly before or after the UV unit?
I've got this question a lot, and there are pros and cons to both. And I guess what I would say first off is follow the UV manufacturer's instructions. And I'll give you my 2 cents worth on why I put it where I put it. So first of all, the purpose of the solenoid is to provide a physical barrier that prevents bacterial or microorganism migration past our disinfection point when the lamp is off. So if we have the system off for any reason, there's an alarm, power outage, whatever, bacteria cannot swim past our point of treatment. Now, if we, in theory, were to put the solenoid on the inlet side, there is a risk that if there is a power failure right now, that not all of the bacteria in the chamber or microorganisms have been fully inactivated. Some of them have received a full dose, some of them have received a partial dose. It's really hard to say what level of dose they have all received. So if my physical barrier is on the inlet, I mean, that's great in that it helps prevent any completely undisinfected water from or microorganisms from entering the chamber or swimming past it. but it wouldn't stop any microorganisms that are currently in the chamber but not entirely inactivated from getting into my downstream pipe. So if I was to move my solenoid to the outlet side of the UV chamber, I would have that type of physical barrier. So in my view, the outlet side is superior. And preferably before any blind corners. So as soon as we get around an elbow, we have essentially a little stub of pipe that is not very well protected. If you had, say, 6 inches or even a foot of straight pipe, and then your solenoid, you're actually quite well protected because a lot of UV light is going to shine down that pipe during the warm-up cycle of your lamp and disinfect that. So it's not like it has to be immediately on the output of your UV unit, although arguably that would be best. But it wouldn't be good to have 3 feet of pipe, then an elbow going up and another 2 feet of pipe, and then your solenoid valve there, because again, you could have microorganisms that get into that downstream pipe. There is one argument for having the solenoid on the inlet side of the sterilizer, and it's related potentially to the system shutting itself off in the event of a catastrophic leak. So the one instance where that could occur with certain UV models is if there was an instance where the UV sleeve was to shatter for some reason. And I can honestly say I've never encountered this personally. The water would then contact the lamp. It would cause a lamp failure alarm, so the lamp would short. That alarm would cause the solenoid to close, and it would shut the leak off. Otherwise, you could potentially have water leaking out into the treatment room. In my view, if you're worried about a leak in your treatment room, you should either have a leak detection system or a floor drain or some containment to address that in another way. I don't think you should do that with a solenoid. I think a solenoid should be there to protect you against microbiologicals. So that's my 2 cents. Other manufacturers will give guidance that is different than that related to their equipment. I guess the ultimate recommendation would be to follow the manufacturer's advice, and in the absence of that advice, probably the outlet is a little bit of a better choice.
That's a great answer, thank you. Another question from Sam Fry. We use vinegar to clean the lamp sleeve. Is this sufficient? Is CLR or Lime Away better? Is vinegar not good?
Yeah. Another good question. So the only problem with vinegar, I mean, it's a weak acid, which is, similar to CLR. CLR is a little bit stronger, and both of them will remove the types of deposits that we're concerned about. CLR will probably work a little bit better in that it's a stronger acid, but the problem with vinegar is that it is an organic acid. It has an organic base. So it could theoretically leave an organic residual behind that could absorb UV light. So our preference would not be to use vinegar. Some people use alcohol as well. They like the fact that alcohol is kind of self-drying on the sleeve. But alcohol has, again, an organic base to it, so it can leave a residual that can inhibit some UV light transmission. So CLR, Lime Away is a decent alternative. We want to be a little bit careful about really strong acids. I've seen hydrochloric acid used before. It's a little on the strong side unless diluted, and it could potentially cause some etching on the sleeve. So my recommendation would be CLR.
Awesome, that's great, thank you. Good point about the organic-based acids. Okay,
so citric would be another example of an organic-based acid, which would have the same problem.
Yeah. Okay, another question from I'm I'm using this mouse over technique to get these questions, so it's a little awkward. Curious, you mentioned not to use lubrication on O-rings for the U sleeves. We have found with the Pro 50 units, they can be quite dangerously difficult to get the sleeves out, but with a very small film of lube on the O-ring are very easy to get out of the reactor. And a
Yeah,
separated lube, of course. And that
right.
comes from Jake Coley.
Okay, great question, Jake. The I want to be a little careful here because personal opinion and manufacturer's guidelines might differ a little bit. You're definitely right that both installing and removing the sleeves on a UV Max Pro and other UV sterilizers can be made easier with a very, very small amount of lubricant. However, I can say that this has been studied pretty carefully by the UV manufacturers, and there is pretty strong evidence that the lubricant is hard to contain and prevent from getting onto other areas of the sleeve in small quantities, and those small quantities can actually have quite an effect on UV transmittance. I do have some tips that may help you work with the UV Max Pro and installing and removing the sleeves. And you kind of mentioned removing as being maybe your bigger struggle here. I want to ask a question, and maybe you can answer it quickly in the chat window for me. Do you have the sleeve removal tool? A lot of people accidentally discard them or lose them along the way. It is a little tool that attaches to the bottom of the sleeve that can help you kind of break the vacuum and the seal of the O-rings when you go to remove the sleeve.
Yes, he says yes, they use the tool.
Yes.
Sorry.
Okay. Good. It does help. I find personally, if you put the sleeve removal tool on the bottom and you put another sleeve removal tool on the top and you start wiggling back and forth, it'll slowly move more and more on each push until it pops free. You may find that technique useful. When you're installing the sleeves, I've found it beneficial to lubricate the O-ring with warm water, or even to pre-warm the O-ring a little bit, and to really massage the O-ring with my fingers into the O-ring groove before I try and do the sleeve bolt. Another technique that I've found really useful is the manufacturer, when they talk about installing the sleeve, talk about putting the bottom sleeve bolt in first. I actually do the reverse procedure. I put my sleeve in, I secure the top sleeve bolt, and then I use the sleeve removal tool and the little screwdriver lever technique that they talk about in the manual for removing the sleeve, to actually push the sleeve up nice and tight against my top sleeve bolt, re-massage that bottom O-ring into its groove, and then that bottom sleeve bolt goes in 1,000 times easier. That technique works really well for me. It may or may not work for you, but that one's been dynamite for us here. Our guys who are really accustomed to it can pop a sleeve out and pop a new sleeve in under 2 minutes using that technique. Granted, the longer they have been in there, also the harder they will be to remove. So the more frequently you do your sleeve maintenance, you'll get more used to doing it. You'll develop a fine-tuned technique, and it'll be easier to do just because they won't be so sealed up in there. If you are going to use lubricant, use very, very, very little, the absolute bare minimum. And that would be outside of manufacturer's recommendations, but I have seen it done, and I do understand why.
It's great. Thank you. It's great that you can share these experience tips, right, with people. The
Absolutely.
last the last questions come from Sean L. He had a couple of comments. One was just, and I did paste this one, and it was right before my question thing stopped working. He just wanted to share some information with everyone about issues he had with his system where UV treatment wasn't working. He was getting lots of alarms for low UV wattage, lamp failure, UV sensor issues. Tried all the troubleshooting and nothing worked. Installation this year, my system installer came out and discussed that the sleeve wasn't quite back in place properly and it wouldn't allow the system to work. So that's what all the alarms were about. There was nothing in the handbook for this. So this is just a tip he's sharing, which is wonderful. Thank you.
So
Something to look for.
great.
Yeah,
I think that's a great point. And it
please.
was one of the things that I glossed over a little bit too quickly in my, in the interest of time. I'm going to go back to that. I don't think I have a lot describing it, but um, so this kind of comes under the possible other causes of a non-firing lamp. And it relates to these reed switches and safety switches. So what a lot of these systems are designed to do is to prevent a lamp from firing when it's not inside its chamber. If you had a UV system from 20 years ago from even what's considered a mainstream manufacturer today, or some of the kind of real low end stuff on the market that's still out there, it's possible to plug a lamp into the lamp harness, plug the system into power, and sit and stare directly at that UV lamp and destroy your eyeballs. The good
Yeah.
manufacturers have prevented that by putting fail-safe mechanisms in place that won't allow the lamp to fire unless the lamp harness is connected properly to the lamp and the lamp is inside its chamber. So there are some of these devices that if they are just a little bit out of alignment, they won't make that proper connection on the basis of, hey, this might not be plugged in correctly, so I'm not going to take a chance. Um, on a UV Max Pro, which I'll speak to because a few people have mentioned it already, the lamp harness actually has a pin that extends down from the harness inside a hole in the UV chamber. Inside that hole is where the little reed switch is. So if that little pin does not go in that hole correctly, it won't flip that little reed switch and allow the lamp to fire. Now, because you could have a left or a right-sided installation, depending on what side your pipes come in at or what side you want to mount your electronics on, you can actually reverse that lamp harness from a right to a left, and there's a separate hole with a separate reed switch on the other side. So if you have a UV Max Pro and it ever seems to be not firing for some reason, it could be related to a faulty reed switch. And you could just simply reverse it and use the other reed switch that's built into your system and see if it fires with it flipped around the other way. Now you do have to take your sleeve bolt and turn it 180 degrees to do that. But it's very, very easy to do. So you basically have a built-in backup without really knowing it. And if you don't have the sleeve bolt turned all the way, we were just had somebody discussing potentially the challenge of installing a sleeve. Well, one of the things that you may have a challenge doing is locking the sleeve bolt in all the way. And if it's not locked all the way, you could potentially connect your lamp harness, but that little pin not go into the hole in the chamber where that reed switch is located, and it won't fire the lamp. So sometimes an extra 1/32 of a turn on that sleeve bolt to seat it fully will allow that to fire. And you're right, if you have an instance like that, they're pretty uncommon, so they're not talked about in any of the details and not talked a lot about in the troubleshooting guides and checklists and that sort of thing. So I apologize that it was a short part of my presentation too, but it is kind of unusual, but it is something that we do see from time to time.
Well,
I'd
clearly it
say I see
happens.
it a couple of times a year, yeah, for sure.
Yeah. Sean had a couple more questions there. I'm going to try
Sure.
and tie them all together because it's sort of similar. So he said his meter reads free chlorine in ppm. What is the equivalent of 0.4 to 1 milligram liter be in ppm? And then he says he Googled it and they're equal.
They
I'll
are
just let
equal.
you comment on that. I don't
Yeah.
know if you have any comments there, but it's
Yeah. So
other people may have come
ppm,
across this.
yeah, ppm and milligrams per liter are exactly the same measure.
Okay.
They're absolutely equivalent.
So good information to know just in case you're reading one thing and seeing something else.
Exactly. If you buy your instruments in the US, they're all going to be ppm measurement, and if you buy them in Canada, they're probably going to be milligrams per liter.
Another one of
Uh,
those things.
yeah,
And
absolutely.
then he had a question that sort of falls into this is his my PHO instructed me to have 2 to 4 ppm free chlorine. Is this way too high?
2 to 4 free chlorine is well, it may be necessary if your chlorine contact time is really low. So to compensate for our limited storage and contact time, because chlorine, I kind of rushed through this and I apologize, but essentially chlorine does not work instantaneously. UV light does. As soon as the water's passed through the chamber, it's done its job. It's very quick. But chlorine is not very fast. It takes time. So after we add the chlorine, we have to put the chlorine into a contact vessel and give it lots of time to do its job. And at 1 ppm, that's about 10 minutes or a little bit more than 10 minutes. And effectively, because we might have shortcutting, we might have to have a vessel that provides for a contact that's even much more than 10 minutes on average, because we got to think about the worst case scenario. So if we have a case where we have really low contact time, the only way we can compensate for that to achieve our same chlorine dosage that we're targeting is to up the chlorine level. Generally speaking, I would say anything over 1 part per million or 1 milligram per liter would be considered high and probably higher than desirable. And the reason for that is that it's going to impact taste and odor. Most consumers would have a negative perception of water that had more than 1 ppm in it or 1 milligram per liter. However, in order, if you don't have a lot of contact time, in order for the chlorine to do its job, you may need to provide chlorination that is that high. You may also need to provide chlorination that's high in order to get the 0.2 chlorine residual at the end of your distribution. If it's 5 miles away, especially, or through a long distribution pipe that has old mineral buildups in it and that sort of thing, chlorine is going to continue to dissipate between your water treatment plant and your customer at the very, very end of the line. So sometimes to get it at those levels at the end of the line, we have to chlorinate pretty high up front. So that could be why you're getting those recommendations, is in order to achieve those other objectives, you have to. Now, I would certainly say if those factors are not in play, you're not having problems creating residual at the end of the line. For instance, if you're getting 2 or 3 or 4 parts per million at the end of your line, and you have suitable chlorine contact, such that you can achieve your CT level at a lower level, then I would say it would probably make a lot of sense for you to reduce your chlorine. A, you'll have more satisfied consumers. B, you will use a lot less chlorine. So it would be desirable from multiple levels.
So I guess it's
Um,
that challenge of,
you have, yeah, you have to
getting the
find out
chlorine as high
why
as you
he's
need
giving
to
that
be,
recommendation.
but not more than you need.
Right.
Sean just also shares that he has 3 large containment tanks for holding, supplies a shower house with 4 showers, 2 toilets, and 5 cabins. In his experience, if I make a chlorine dosage change, it takes a day to a day and a half to change through the system. I'm not sure if
Yeah.
that, yeah,
So I mean
sounds.
that to me is suggestive that the retention time within his system is long.
Mhm.
So he's very likely not having any problem meeting his CT requirements, with the storage that he has. Um, one of the things I could send you to do a little bit of homework, and I'd be happy to help you look at this in more detail, would be to draw up a little sketch of how the water goes in and out of your different storage tanks, what the configuration of that looks like, and using and your approximate capacities of each. And when looking at the capacities, consider the lowest level that they're at. So, at maximum drawdown, it'll probably be where you turn your pump back on to refill your tanks. How much water do they hold roughly at that point? And then I can do some chlorine contact calculations for you. We can estimate your baffle factor based on your configuration, and we can determine probably pretty accurately whether or not that level can be safely reduced. And if it can, then we can go to your drinking water officer with a plan and say, and it doesn't have to be anything too fancy. This is how we feel we'd like to operate it going forward. And here's our contact time calculation, kind of proving out the science behind this. And here's our safety factor that we're building into this. And you may be able to reduce those levels.
He
But
he says that you designed his system at Egan Lake Resort.
oh, at Egan, okay.
So
Yeah, so you're probably running high. I can look up when we did the construction permit, or where the dealer did the construction permit application. We would have pre-submitted a proposal for how the chlorine contact was to be run at the end of the contact time, or the end of the contact vessels. And I will guarantee it was not designed to be up that high. The maximum we ever designed to is 1 milligram per liter.
that's good information.
Yeah. So you should be able
That's
to reduce that a lot.
so you guys should talk.
Yeah.
I don't have any more. Yes, he says he'll email you. I don't have any more questions. It sounds like Sean has some questions for you, though. I did share your email address in the chat. I wanted to thank Grant. Thank you so much for this talk. There's still quite a few people here listening, so lots of fantastic information. Thank you very much for your time today and for the extra time. And we tested the system, and we now know that it's not going to cut us off. So that's good to know. Thanks for everyone else for attending today, for attending way over time, but clearly enjoying it. I will post the video, and I usually get the video and the presentation posted within a couple of days. And Grant, I will be able to get all the questions in text form to you through email, and we can talk offline about answering what we can do to answer them and cycle them back
Sure.
for people. But I'm glad that everybody, as many people who were able to hold on were and got the full explanations from you, because it was really great. Thanks again for your time, everyone. You will be getting a certificate for those who are looking for that CU certificate, it should be in your mailbox within a day. If you don't get it, please email info@smallwatersystemsbc.ca and we will sort that out. And just to remind you, we will be having another webinar next month on July 19th on well operations and maintenance best practices. So keep an eye out for that.
Excellent. I'd like to thank everybody as well, and thank you, Natasha and Mike, for organizing everything. It was very smooth. Thank you.
Thank you. That was great. Another great presentation. So
Yeah, thanks, Grant. That was awesome.
Have a wonderful day, everybody, and feel free to reach out if you have any questions. I'd be more than happy to help.
Okay. Okay, take care, everyone.
Thank you.
We'll
Bye-bye.
see you next month. Bye-bye.